Hello, welcome to the SETI colloquium series. Today, our talk is closer to home in space, but very distant in time. Our speaker today is Michael Lesher. Michael got his undergrad and master's degree at Indiana University in Bloomington. Then, after working in the industry, he got his PhD from West Australia University in Perth. He taught in Alabama, and now he is professor at the Laurentian University in Ontario. And today he'll tell us about the high temperature volcanism on Earth, physical volcanology, mineralogy, and geochemistry of Komatiites. Thank you.
Thanks very much. So first of all, if some of you aren't familiar with Komatiites, they're basically ultramafic volcanic rocks. They were predicted by Bowen, a very famous experimental petrologist in the earlier part of the last century, to not exist, that it was impossible for the Earth's mantle to create such high magnesium, high temperature rocks, but they were subsequently discovered and have been of interest since. They are characterized by very high magnesium contents, which, as we'll see, is proportional to their temperature. They have very low silica contents, unlike most other crustal rocks on Earth. And they have extremely low abundances of highly incompatible lithophile elements, meaning elements that when you melt the mantle, these have low abundances of those because we've melted so much of the mantle that they've been diluted by melting olivine in the mantle. They contain abundant olivine, unlike a lot of crustal rocks. They're characterized by particular spinifex textures that I'll explain and show you some examples of. There are some intrusive equivalents, so not all of them are volcanic, some intruded beneath the surface at various levels. And most examples are Archean, so greater than 2.5 billion years old, but there's a few younger examples, although they're not really the same sort of thing as we'll see in the Archean. These are some of the localities. I guess I've got a pointer here, so which I didn't try, so I'll try this one. There, got it. So I'll be talking about some of the ones in Western Australia. They were first discovered in the Barberton Mountain land in South Africa and subsequently in Zimbabwe, some very beautifully preserved ones there. The ones I've worked on most extensively are in the Yilgarn Craton of Western Australia. They're also beautifully exposed in the Superior Province of Ontario and other occurrences, basically in many Archean greenstone belts. I'm having a slide malfunction here. Yeah. There. Ah, good. Okay. So I'll be talking about a few localities in Western Australia. Kambalda down here is where there's been a particularly large amount of work done. These are the Barberton Komatiites in the Barberton Mountain land here. Zimbabwe, the ones Ishvani here are the particularly well preserved ones. And here at Alexo and Dundonald are some particularly nice ones just a little bit north of Sudbury. Yeah, I guess I'm pointing at the wrong direction. Okay, so if we look at how their compositions vary with time, this is a plot of magnesium content against age, and this is proportional to temperature. And we can see, for example, that in the Archean, greater than 2.5, they're typically more magnesium with MgO contents up to about 33 or 34, much greater than in the Phanerozoic and Proterozoic and Phanerozoic. So something very fundamental happened at this point, and it's long been speculated that this represented a change in the thermal structure of the Earth. And this now shows this MgO against temperature. So these are the aluminum undepleted Komatiites I was referring to. There are actually other flavors that I won't talk about. There's not enough time for that. And these are the eruption temperatures. So the primary eruption temperatures are shown here. Some reference things, Gorgona Island off of Colombia. The Pyke have that sort of eruption temperature. And Hawaii, Ongtong Java is an oceanic plateau. Iceland, I think you're familiar with that. These are down in this sort of range here. if we look at what the potential temperatures were in the mantle, in other words, if we took the mantle and decompressed it, then that corresponds to these sorts of temperatures in the mantle. So very, very high temperatures, and there's this abrupt change then basically from very high temperature things down here to much lower temperature things at Gorgona, Hawaii, and the other things, all happening at 2.5 GA. There are three possibilities for what happened. One is that in the Archean we had whole mantle convection, and in the Post-Archean two-layer convection. So we basically had the whole mantle convecting as one unit at that time, and then we introduced a boundary layer, for example, the 660 kilometer discontinuity at that point, and that changed the temperatures at which things were erupted. Another possibility is that we had the reverse, two-layer convection in the Archean. In this case, it would be some dense residue, garnet-rich, of the early magma ocean, and that then in the Post-Archean that disappeared. We don't see evidence of it now, and so that's speculation, but this would change the path along which magmas would rise along the adiabat. And finally, the third model, which is the one I'm most in favor of, is that what we had a change in was, in fact, the formation of a boundary layer along the core mantle boundary. This is called D double prime by the geophysicists. It's recognized today geophysically, and the idea is then that if we had a change in the boundary layer at that, then this would affect the path of adiabatic melting. This has been modeled by Campbell and Griffiths more recently, and the idea is that the temperature across a narrow boundary layer compared with that's a pretty weak pointer, across a denser and thicker boundary layer would influence the temperature at which things come up. Another thing that's very interesting about komatiites is that their platinum group element geochemistry records a secular change in the geochemistry of the platinum group elements, such that the Archean, the older Archean ones, are depleted in platinum group elements compared to the younger Archean ones. So these are the most common ones here at 2.7. These are the ones from Ruth Well in the northern part of Western Australia, parts of South Africa, and these older ones are all depleted in PGEs. And the interpretation of this has been, in fact, that this records the slow mixing of the late veneer back into the mantle, and therefore the time that it took to homogenize the mantle after that. So what are their physical characteristics? Well, they have very high temperatures, up to about 1640 or more degrees centigrade. They have high densities, very low viscosities, high specific heats, high heats of fusion, and something that's particularly important in how they crystallize, a very large interval over between the liquidus and the solidus. And the other thing that's important is that they're derived by very high degree partial melting in the mantle, and so we're melting basically everything but olivine, and they therefore record the trace element composition of the Earth's mantle very faithfully. So modern basalts would have erupted, and this is an example from Hawaii I modified on the right, would erupt and they're red and yellow hot, whereas Archean komatiites, in fact, would have been much hotter. They might have been white hot when they erupted. So the consequences of all those physical characteristics is that they form very voluminous eruptions because we're melting huge amounts of the mantle, up to 50% instead of, say, 10 or 15% for a modern mid-ocean ridge basalt. They would form highly mobile flows because of their very low viscosity, and these would allow them to flow very long distances over very gentle slopes. They'd be much faster flowing, for example, than a Hawaiian basalt, capable of thermomechanically eroding their wall rocks and substrates. And we'll see this is important later on in influencing some of the changes in their chemical compositions and in making certain types of ore deposits. And they're capable of crystallizing and accumulating very large amounts of olivine prior to solidification. So in terms of phase equilibria, komatiites crystallize olivine over a very large interval. At some point, at about 20% MgO, they're joined by chromite on the liquidus, and then they crystallize down successively to form clinopyroxene until they reach the pyroxene plagioclase cotectic at about 1180. If the flow is thick enough and it cools slowly enough and fractionates enough, we can actually get gabbroic rocks, basaltic gabbroic rocks forming from komatiitic parents. And of course, if we contaminate them by eroding some of the footwall rocks, we can crystallize orthopyroxene. So this is a diagram of temperature versus liquid. There's a couple important things. The first is that the liquidus here is very steep, and that means over a very large temperature interval, we're actually not crystallizing very much, and it's only olivine. And then what happens is that the slope of the rest of the liquid is very flat, and so you get a very large amount of crystallization over a very narrow interval. So this part of it, it's actually solidifying very quickly, and here it's taking a very long time to solidify. And this allows them to flow for a very long time, even as they're cooling, and it allows them to crystallize large amounts of olivine. The crystallization textures that are developed depend a lot on how rapid the cooling is. If the cooling is very rapid, you get feathery textures or hopper crystals that have holes in them. Skeletal crystals are sometimes called. And then at lower amounts of supercooling and lower amounts of cooling rate, they form more equant crystals. These give rise, these more dendritic textures, to something that's called Spinifex, and it's actually named after the Trotia spinifex plant in Western Australia, where the term was first coined. This is the type locality at Barberton. So this is the top of the lava flow here. There's a lens cap for scale, and this is a flow top breccia. So these are rocks that have been cooled by the seawater and fractured, and they may even move as the lava flow is being emplaced. Beneath that is a Spinifex zone, which isn't evident in this photo, but I'll show you a close-up in a second, and it's underlain by an olivine cumulate zone. So this lava flow is differentiated. It's crystallized some olivine that's settled to the bottom, and the rest of it reached the point where it cooled very quickly and formed the Spinifex texture. So this is the Spinifex texture. These are little blades of serpentinized, now I'll talk about the alteration in a bit, serpentinized olivine. And so each of these little light-colored bits was an olivine, and in between was glass. About the composition of a basalt, actually, after it's crystallized the olivine. They're a little bit better exposed in Ontario. This is from Pyke Hill. This is the top of the flow up here. You notice it's not a breccia, but it's all fractured, so the top is just cooled and contracted, a bit like mud cracks, I guess. The size of the olivine crystals get larger and larger as you go down, so these crystals are quite large. These are small, these are more random oriented, whereas these are more platy. And then underneath this, and this is peculiar to this locality, is a zone where the olivines are little stubby crystals that are oriented horizontally, called a B1 zone. And then underlying that are more cumulates, like we saw at Barberton. This is a close-up of some of the Spinifex textures. So these are basically olivine plates, and they form just radiating cones that nucleate on each other, and they grow basically down and fan downwards. And then the interstitial areas, as I mentioned, are filled with glass or former glass. This is a photomicrograph from this area. This is the olivine here. You can see they've got skeletal textures. And then in between this material that's black, because I've crossed the polarizers on the microscope, is the altered glass. So it's not actually glass anymore, but it's so fine-grained that it doesn't pass the doubly polarized light. These are some more textures. They're actually quite beautiful. These are just black and white ones because they come out of the Komatiite book. But all the various types of hopper crystals, these are Spinifex plates, and then in between are beautifully preserved little pyroxene crystals that are growing perpendicular or slightly oblique in this case, to that, and then chains of pyroxene crystals with interstitial glass. These are pyroxene fans, so these are little sprays that grew very quickly. So this is all related to nucleation rates too, how difficult it is to diffuse elements in the magma, and whether the crystal prefers to grow from an existing crystal or to nucleate in a new location. Some more textures. These are more some of the cumulate rocks, so these are now becoming what we call orthocumulates. They've still got a lot of interstitial glass in them, but these are all olivines or serpentinized olivines with different habits depending on the rate at which they cooled. This is from the Murphy Well outcrop in Western Australia, which is about 100 meters thick of that sort of stuff. So everything crystallized all at the same time with that particular texture. Yeah, sorry about that. So these are all a couple or 5 millimeters across. I'm sorry I didn't put that in. Yeah, so these are probably 5 or 6 millimeters across right there. Yeah. Now, unfortunately, but inevitably I'm afraid, because olivine is a high temperature mineral, what happens when you cool the rock below the temperatures that are olivine is happy, it rapidly converts to serpentine and the glass converts to chlorite. The pyroxene is actually a little happier and tends to stay around a little longer, but eventually it succumbs and turns into tremolite, which is an amphibole. And what I've done here is just a summary of the different rock types. And so the more magnesian rocks with more olivine in them are up here, and the ones that are more basaltic are down here. And these are some of the changes in the mineralogy. So this is the igneous assemblage, olivine and chromite with very little liquid in a dunite, which is an adcumulate rock. And then as we add more and more liquid and less olivine, then we end up with olivine and chromite and glass, olivine and glass, and clinopyroxene and glass. And we can have interstitial areas of these rocks that have clinopyroxene in them, as we saw. As we undergo metamorphism at very low, low to medium, or medium to high, and depending on whether we have water around or carbonate, then we can form a variety of different assemblages, ranging from, for example, antigerite, which is one of the 3 serpentine polymorphs, brucite, Fe-rich chromite, magnetite, tremolite, and chlorite, to, for example, talc, magnesite, magnetite, and chlorite. And I won't repeat all the rest. Steve Barnes has summarized this. I think it's Steve, yep. In terms of temperature, and these are the same rock types I mentioned. So this is a komatiitic basalt over here to a dunite. And so you can sort of draw some boundaries in here. And when you actually look at the rocks in the field and identify the minerals, you can pretty much guess what the rock type is based on the mineralogy. So this is with a low mass fraction of CO2. So these are the hydrous assemblages. So we see a lot of tremolite, chlorite, and olivine preserved at these temperatures. At lower metamorphic grades, we get serpentine, tremolite, and chlorite in sort of these range of rocks. If we add CO2, then we end up getting magnesite, which is the magnesium end member of the carbonates, dolomite, which is a calcium magnesium carbonate, and various other things, and at high temperatures, things like diopside and so forth. Just to show this in terms of temperature and XCO2 space, so these are now very high CO2 activities, probably unrealistic, but the point is that serpentine and carbonate are stable down here. We can actually get metamorphic olivine formed down here. So for example, if we serpentinize it on the seafloor and then metamorphose it regionally by burying it under a mountain belt, then we can generate metamorphic olivine, which has very different textures and geochemistry and habits than the igneous olivine. I think I'll skip that one. So here's some examples of some more altered rocks. These are from Kambalda. You can still see the Spinifex plates. You can still see the pyroxenes. The little crosses in here are actually dendritic chromite. So even at this stage, when we've metamorphosed it to probably 500 degrees C at 2 or 3 kilobars, we've preserved all these delicate textures. This is a more platy one. We can still see the pseudomorphs after the pyroxene in here. These are now serpentinized olivine. Now here's some fresh olivine. This is an orthocumulate rock, so the interstitial material used to be all glass. It's now a fine-grained mixture of pyroxene and glass. There's a few chromites. The rest of the black is magnetite forming along the margins of the olivines during the serpentinization process. And then these olivines are brown because they actually contain ultrafine exsolved inclusions of chromite. Chrome was soluble in the olivine at high temperatures, and it wasn't when it was metamorphosed. This is a particularly interesting one. This is a crescumulate olivine. If I were to rotate the stage in doubly polarized light, this would all go extinct at the same point. And that's because that's one crystal. And some of these crystals are about that long, a meter long, and they all go extinct at the same time. They're basically big coral-like growths of olivine, and they're given the texture a crescumulate after some textures in the Skaergaard intrusion in Greenland. Sorry, mind blank there. Oh, and finally, here's some very large coarse olivine with some former melt inclusions in it, with a variety of different habits here, and some still starting to show a little bit of irregularities in shapes. The thing that's important about this is that, and I'll show you this geochemically as we go on, all this olivine actually crystallized in place. It wasn't transported, it crystallized in place. Okay, I'll show you a couple geochemical profiles. The key thing we use geochemistry for is to determine whether there are variations in the composition of the olivine. The relative thicknesses of the spinifex and cumulate zones is important. That tells us whether or not there was any olivine being carried or not, or whether it accumulated in place. We can get some idea from the magnesium contents and other trace elements of how the flow crystallized in terms of the relative timing of growth of spinifex and cumulate zones. And chromite can give us some additional information about this. So this is a profile through one of the host units at Kambalda. This is an ore deposit I'll talk about later on. And there's a change in scale here. So this is 20 meters and this is 2 meters. And the upper part of the flow, the magnesium content in red here, decreases systematically, and then it increases abruptly here and is very homogeneous over this range in here. So these are compatible elements. Chrome basically does the same thing, which is in the gray. Sorry, there's the scale for chrome up there. And nickel follows magnesium very closely. So all these things are in the olivine, and so they're tracking the olivine. These other elements in here, titanium, calcium, aluminum, and iron, are showing the reverse relationship because they're more abundant in the liquid that's interstitial to the olivine. So we get a couple things from this. The first is that we've got, basically 100 meters worth of cumulate rocks. That's a lot of olivine. And so there was a big debate early on whether that was all carried in with the magma and deposited, or, as I'm going to argue, that the magma flows through, crystallizes some olivine, leaves, more lava comes in, and that it's a dynamic, continuous process whereby we just accumulate olivine. I'll show you why I think that in a second. And part of the evidence for that is not only the crescumulate textures, you're not going to transport those, but also we have systematic changes in, I think I've lost the pointer, in the compositions of the olivine. So as you can look up at the top up there, in the orthocumulate rocks up there, the little purple line, we have a change from orthocumulates to mesocumulates to crescumulates, and the composition of the olivine is changing. In a magma that's 1600 degrees carrying olivine, there's no way that there wouldn't be a diffusional reequilibration, and that if we were carrying it, that all the olivine would be the same composition. What's happened is it varies in composition, it varies in texture, and that's telling us that this growth is happening while the lava channel is active and cooling as it's flowing. And it was a very long duration eruption. So I'm not going to read all these. I just want to point out that komatiites form a wide range of lithofacies. And by that I mean the textures of the rocks. And so we've seen some examples of that. But there's a wide range in textures because different parts of the flow were cooling at different rates. The upper parts were cooling extremely fast, chilled by seawater, whereas other parts of the flow were cooling very slowly because lava was still trickling through the system. They also form a wide range of flow facies. I'll show you some examples of these, ranging from pyroclastic rocks to pillows and lava lobes, and then a wide range of differentiated sheet flows and lava channels. And then finally, we can put all these together and generate what are called facies assemblages to help us understand what komatiite flow fields would have looked like. And so we basically have lava lakes, there are lava channel or conduit complexes, there are sheet flows that then have channelized parts within them, and then of course we can have compound flow lobes like we do in modern basaltic systems. When we look at these facies environments, we can characterize some as being near the vent, the proximal pyroclastic and lava lake, and there's been mineralization reported in those. I'm actually an economic geologist, so I work on the rocks so I can understand the ore deposits. Others are fairly proximal, representing these sorts of things I've just described. And then as we range to distal or mid-distal, we get other facies out here. It turns out that the mineralization occurs in very specific locations, and I'll show you that. And we never find mineralization in lava lakes or in distal situations, and I'll explain why as we go along. So this is a pyroclastic komatiite. This is from Monroe Township, so not too far from the Pyke Hill outcrop. And so all the green material would have been volcanic glass. All these would have been fragments, and this is now highly altered, but it's preserving the original textures of the rock. It's a little bit flattened and stretched. That's what happens when rocks are 2.7 billion years old and get tilted around a little bit, but it's in remarkably good shape for being so old. This is an interesting breccia from in the same neighborhood, actually across the road from Pyke Hill, way back in the bush. And this is Spinifex textured. You can probably make out these lines in here, but each of these fragments has a different orientation. So here what's happened is that the flow was flowing along, it crystallized the Spinifex zone, and then it either inflated or it collapsed or there was a breakout or something like that, and we formed this breccia composed of the preformed Spinifex rocks. This is another example of that. It doesn't show it, it's not, I should have maybe outlined some of these. I'll let the pointer rest, but you can see some of the fragments in there are different colors and different textures. And if we look at that in thin section, you can see there's all kinds of different fragments in there, some of which have very fine-grained random Spinifex textures and others which are more glassy. And so this is another example where we've ripped up the upper part of the flow top and transported it in some location. This is an ultramafic explosion breccia. The photograph isn't great. The lighting was very bad that day, and the Russian guard we had with us didn't let us spend much time in the pit where this was located. But each of those fragments is a different type of what's called a ferropicrite, and it's just an iron-rich version of a komatiite. But this is the same sort of thing, and this is effectively a volcanic vent then. These are some lava lobes, again from Monroe Township. So each of those is sort of a little lobe of lava that's spreading out. So more like what you see at the very distal ends of probably submarine of Hawaii, down from where things flow into the ocean. On a larger scale, we can begin to see that we can form larger flows. And this is an example from the Cape Smith Belt in northern Quebec. And the units that are important, these are a bunch of pillowed basalts, and these are another type of pillow basalts. These are tholeiitic and komatiitic, if you have a little geology. And what's interesting about this is this unit along here, which is the one that contains the mineralization. And where the mineralization is, you can see the unit is very homogeneous. It's formed of peridotite, which is basically a cumulate komatiite, so lots of olivine. And then where there's no mineralization, the intervening areas, the blue are gabbroic rocks, meaning that that part of the flow is very differentiated. So we have blue over the peridotite, so that's a very differentiated flow, and there's no mineralization. And then if you go around onto the other flank, we see the same thing. It's thicker because the dip is less, so it's exaggerated thickness, but the same sort of thing. And we even have some sediment on top of that in gray. So what happens is that this is a big sheet flow flowing along, and certain parts of it are channelized, and they're flowing more rapidly, and they're able to melt the underlying rocks and form the mineralization, a process I'll explain as we go along. So that's a channelized sheet flow. And then further along in the belt is at the Katnick area, we have basically an isolated lava channel where it didn't have a big sheet flow flanking it. It's just basically a lava channel. And you can see that's shown here in purple. These are those overlying basalts in the light green. That's an overlying thin flow in purple. The blue underneath is a layered gabbro, and you can see the peridotite successively cuts down through, starting over here, down through these thin other rocks, sediments and gabbroic rocks that are here, cuts down, successively cuts its way down completely through the gabbro, and then at that point forms low areas where the sulfides collect. So this is an example of thermomechanical erosion. I'll show you some photographs of what that looks like in a second. So we think these things are analogous to the lava channels on Hawaii. So this is Pu'uo'o. If you've ever been there, this is a USGS photo. This is the one I showed you earlier. And the idea is that these are lava channels. They sometimes spill over, but these aren't sheet flows. Sheet flows would have covered much wider areas and then become channelized within that. So these are isolated lava channels. So if we put all that together, we actually see what happens is komatiites form an amazing range of facies. And it depends basically on the amount of differentiation that the flow undergoes. So whether we get separations of cumulate zones and more differentiated rocks. So that's the scale on the bottom. And then along the top is the amount of olivine that's accumulated. And it turns out that the units that have the most olivine are the ones that contain the most mineralization. And that's because those are the most channelized rocks. We need a lot of lava flow to bring in all the magma from which that olivine crystallizes, especially if it's dynamic. So it needs to last a long time so we can accumulate a large amount of olivine. This just shows that relationship in terms of the thickness of the unit. Now, some of these units are very thick. They can be up to a kilometer thick. That's a pretty thick lava flow. Those are thicker than the Columbia River basalt flows, for example. And then this is calculated by mass balance, the amount of excess olivine. And the mineralized units are thick, and they tend to have lots of olivine in them. If we look at the flanking sheet flow facies of these channelized units, then they have the same amount of olivine accumulated, but they tend to be thinner. And the differentiated units, the ones that don't have a lot of excess olivine in them, the bulk composition of the whole flow, if we were to sample through it, is the same as the liquid, are basically down here, and they can occur in any thickness. But of course, they're not channelized because they're so strongly differentiated. So there have been lots of flow field models. I won't dwell on this. Some have focused on lava channelization, some on lava regression, some on lava sill complexes that form, and some on whether or not we could have had analogs for sinuous rills in these systems. And so most of these models are based on looking at Hawaii, which is unfortunate because the slopes are much steeper, the lava is much more viscous and so forth, but this is probably the closest analogy to what we have to look at. Maybe some place like Ongtong, Java would be better, but that's submarine. It's a submarine plateau. So most of the models are built on that. And so what we end up with something look like this. There's a feeding fissure. In some cases, you can have mineralization in the feeder. There are channels that feed the distal parts of the flow, lava lobes and things like that. And what happens is that the mineralization is found exclusively in the channels, and they can be thin channels or not so thin channels, very thick. So they can be kilometer thick or so up in here, and maybe only 100 meters or 50 meters or 30 meters thick out here. So these are some mineralized examples in these areas, and some mineralized areas down there. I'll be talking about some of these as we go along. Okay, now I just want to mention very briefly that there are subvolcanic equivalents of these, and there are a couple criteria that have been used to determine whether we have these or not. So very diagnostic is whether or not you have a flow-top breccia, because you can't form that if you inject it underneath other rocks. Polyhedral jointing, like we saw in Monroe Township, where it's sort of the mud crack effect, that's fairly diagnostic. You don't find that in sills or a ropey flow top, which we almost never see. Diagnostic of intrusion is when you've got a cross-cutting upper contact. I'll show you a red herring in a second. Or baking over the overlying rocks. That's very diagnostic. If you've baked the overlying rocks, then it had to be intrusive. Turns out Spinifex texture, yes? I'll show you. That means they contain iron, copper, and nickel sulfide minerals, was the question. That's what I mean by mineralized.
So it's mineralized with those sulfides, not necessarily missing minerals.
Yeah, no, this is sulfide. Yeah, sorry, this is an ore deposits term. When it's mineralized, that's the good stuff, and when it's unmineralized, that's the bad stuff. And also non-diagnostic is a cross-cutting lower contact. As we'll see, komatiites can cross-cut underlying rocks, whether it's a sill or a lava flow, and of course, baking of the underlying rocks is non-diagnostic. So here's an example. This is from Hawaii, and I want you to imagine this is basically a lava tube that was crusted over, and it squirted lava out, forming these little things that stick up along here. If you were to cover this by another lava flow, and you were to then tilt this and glaciate it, like we see in Ontario, you would see this sticking up into the overlying unit, and you would say that's a cross-cutting relationship. It's not. That would only work if this baked the overlying rocks, right? So the field relationships here are tricky, and a lot of the interpretations that have been made in the literature are probably wrong because they don't have all the criteria for intrusive versus extrusive. The reason I dwell on this is that, as I mentioned, Bowen said you couldn't erupt ultramafic rocks. And so there's been a big pendulum that's been swinging back and forth where some people have regarded all komatiites as being intrusive for a very long time, and then they all became extrusive, and then finally there's a bit of a balance now where we recognize that both are present. And I'll show you a couple good examples. So this is a Spinifex textured vein. That's a Canadian penny, which is the same as yours, although we don't have those anymore, so that is an antique now. And that's a perfect Spinifex texture, and this is clearly a vein cross-cutting this actually accumulate komatiite. So Spinifex texture is not diagnostic. This is going to be unintelligible, but this is an outcrop map to show you that we actually map the rocks. And these are all different types of komatiites in here, and there's interflow sediments. And I'm going to hone in on that, and just to confuse you further, I'm going to flip it upside down. And this is the outcrop that was mapped. And so this is the unit in question. The upper contact's up here, the lower contact's down here. So this is an underlying unit, I'm going to call it. And this is the unit we looked at. And it has Spinifex texture on the top and cumulate on the bottom, and it has a nice B1 zone. So this had been mapped for 20 years, ever since we realized there were komatiites, as a lava flow, right? Wrong. So what happens is you look at that contact, it's right through here, and this is weathering, unfortunately, but that's what comes from sampling outcrop. And you can see these are the cumulate rocks over here. So every one of these is a little bit of olivine, and then we've got these coarse crystals growing dead on that. That can't happen in a lava flow. There's no flow-top breccia. There's no random olivine spinifex. There's no platy spinifex. We just have these hopper crystals. So that's an intrusive relationship. High level, but intrusive. Okay, the depth of emplacement of intrusive komatiites is controlled by the tectonic environment, the density underlying crust, the rheology of surface rocks. I don't want to dwell on this, but I just want to show you that there are examples of intrusive komatiites. This is the Alexo mine area. I'll show you some photos from there in a second, and a couple other areas. That outcrop I just showed you was an area called Dundonald Beach. And what happens is that at some particular point in the stratigraphy right here, all these things are extrusive and all these are intrusive. So this komatiite is intrusive, that komatiite's intrusive, this whole unit here, which is composed of multiple units, is intrusive, and these are all intrusive. So 10 years ago, those were all extrusive, now they're intrusive. Okay, let's talk about thermomechanical erosion. So as first suggested by Ewan Nisbet in the first Komatiite book, depends mostly on flow rate, flow duration, and nature of the substrate. Also its state, whether it's consolidated or unconsolidated. And lava channelization is critical. We only find it where lavas are channelized. And it's been mathematically modeled by Huppert and Sparks in a landmark paper, and then by me and one of my students, David Williams, who's at Arizona State, in several papers since. So the idea here is that and the lava is flowing in this direction, so you're getting more melting closer to the eruption site and less as we move forward. We need to allow for loss of heat through the upper crust. We need to worry about what the thickness of the crust is. We need to worry about conductive and convective heat loss into melting the substrate. And there's a compositional change that occurs when we incorporate the underlying rocks that we need to take into account. So I think I'll skip over that. Just to show you, we've treated this fairly seriously. We have terms in our model that allow for the crystallinity. This affects viscosity. So the temperature of the liquid and the temperature of the solid. We have to take the bulk viscosity into account, of course. And when this viscosity exceeds a certain amount, then we have to treat it differently. But when it's less than this, then we can calculate the bulk viscosity using this term. There's other terms for when there's more olivine around. We have a flow velocity that can be calculated basically from the gradient, a friction coefficient that has to be allowed for. We have a Reynolds number in there that allows us to determine whether we're in laminar or viscous, turbulent flow. And we have a thermal conductivity term, of course, for transferring heat into the substrate. We have Prandtl numbers to worry about, which are ratios of viscosity to kinematic viscosity, forced convective heat transfer coefficients. We can calculate the lava erosion rate. And then most importantly that we've done is actually have terms for allow us to incorporate the amount of assimilated substrate and its effect on the viscosity and density. We are particularly concerned with the steady state crustal thickness because that's something we can measure in the field. And so then we solve this equation here, which incorporates those terms I've just mentioned as a function of the downstream distance. And then we worry about keeping the steady state crustal temperature in balance on all this. The main thing that allows us to produce a model is very different from the ones that have been done in the past is that we've kept track of the mass that's been assimilated and the olivine that's crystallized. If you assimilate something, you cool the magma and you have to crystallize olivine. So the two go together. If we flow over an unconsolidated substrate, we have several more terms that we have to put in. We have an energy required to disaggregate the ground, and basically that means if we've got unconsolidated material with seawater in it, we vaporize the seawater, and that disaggregates the unconsolidated sediment. And then we have a term that allows us to actually mechanically erode that material in there. So we can model different kinds of substrates that way, crystalline or otherwise. So these are some results for those different models. We've done this for basalt because that's what the rock flows over at Kambalda, consolidated sediment and unconsolidated sediment. We've kept the crust the same because the crustal thickness is the same at Kambalda. We've calculated the distances that happen so it can flow further over a basalt whereas it incorporates more unconsolidated sediment, becomes contaminated, increases the viscosity, and can't flow as far if it's unconsolidated. We end up with roughly the same flow thicknesses, which we've modeled a 10-meter thick flow here, but we've also modeled 50 and 100-meter thick flows. The erosion rates are very different if it's unconsolidated versus consolidated. Different channel depths because of that, different amounts of contamination, and the magnesium contents of the resulting magma are a little bit different. So the results, the bottom line is so a 10-meter thick komatiite flow can flow up to 300 kilometers. The previous estimate in the Huppert and Sparks model was actually 2,000 kilometers, which is probably unrealistic. And that's because they didn't take into account the contamination effect on the viscosity and about 5 other terms. Up to 50% of the flow length was in the transitional or laminar flow regime. So in other words, 50% of its turbulent flow, full turbulent flow, whereas the latter half is transitional or laminar. Thermal erosion occurs up to 160 kilometers from the source. And with all else equal, of course, there's different erodibilities. As everyone would predict, unconsolidated sediments are greater than consolidated sediments, unwelded tuffs more than welded tuffs. That's the difference between whether they heat themselves together before they fall, felsic rocks more than mafic rocks, and rocks that have crystals in them and can melt at eutectics melt more than aphanitic rocks, or more easily. If we add sulfides to this, then things melt even more readily. Okay, this is sort of the cartoon how this happens. We originally have these embayments. That's a different story, but they have sediment on them. That's this white layer here, and as the lava flow flows across, it melts that sediment, and I'll show you some examples. In some cases, it can even melt its way down in far enough and begin to melt laterally. So just a real quick example now of Kambalda, and then we'll be done. So this is the cartoon I just showed. These are the lateral sediments, which become eroded as we go in. The ores are down on the bottom here of this embayment, massive ores and what we call net textured ores, sort of interstitial ores. Along the flanks, there are rocks called ocellites. I'll explain why those are important in a second. And we can have multiple layers of this. And then finally, we can also see very delicate erosional features. So here's a really good example. So this is the former top of a Spinifex flow. And we're missing the random Spinifex in the flow top breccia because it's been cut down into by the sulfides. And what's happening is the sulfides are melting the interstitial material between the platy Spinifex here, and it's less dense, so it comes up and forms little domes. So those are like little jellyfish. And then the dense sulfides are percolating down. So that's thermal erosion caught in action, snapshot at the end of the process. When we do that, and when we melt the sediments on the flanks, we produce rocks like this, which is basically melted sediment, but it's depleted in all the metals because the metals have stayed behind in the sulfide. So we can look at this geochemically, only one geochemical diagram. This is the bulk composition of the sediment. The sulfide that's in the sediment would plot here with a low nickel content. That ocellite would plot here, and there are also chloritic rocks that I haven't shown you that are residues. And so this is basically an extract diagram. And what happens is that we take the nickel that was in this, and it gets stripped out of the silicate xenomelt and ends up going up into the ore. And then by reaction with the magma, we also deplete some of the magma, some of the rocks nearby in metal. This is actually used as an exploration indicator. So we can see the same thing for iridium, except now on a log scale. So we're a couple orders of magnitude depleted in iridium. And what happens is this barren sulfide scavenges all the iridium in the komatiite to make the ore. So that's the ore formation process. Okay, just a couple quick examples here at the end. We see this at Raglan, which is up in the Cape Smith Belt. This is a gabbro, and these are xenoliths. Some of them are amoeboid shaped, others are more angular, overlain by massive sulfides. So we're basically gobbling up this material. Once it gets up into here, it gets melted very quickly and dispersed, so you don't see anything above that. At Alexo, Ontario, we can see the same thing where the ore is cutting down through an andesite. That's a intermediate volcanic rock, a little more silicious than basalt. And that looks like this. Because this is a hillside, the younging direction is this, but this is the underlying contact there with andesite that's bleached. It basically got heated up and cooked in its own juices. At the bottom of that, now right way up, the komatiteites can burrow their way in, and they actually form little sills on the side here. And what's happening here is that if this had continued, that andesite fragment would have been plucked up and carried into the magma. So this is a combination of thermal and mechanical erosion. Here along the basal contact, we can see now flipped around again, where the sunlight was. You can see the ore migrating in and melting its way into the andesite, and little bits of andesite melt that are floating up in the ore. And of course, the further they go, then they get dispersed. So last slide, just to show you that these are very significant resources. So Kambalda I mentioned is up at the top, Ragland I mentioned. There's a bunch of smaller deposits on the left we won't worry about in gray, but these things have 1 million tons of nickel. And so these things are worth billions of dollars. Sudbury, where I spend most of my time working, is there. It's one of the richer ones in the world. A ton of ore there is worth about, in some cases, $2,000, just 1 ton of ore. One of the many different ore deposits at Sudbury each one is worth about $200 billion in terms of the mined ore. So these are not insignificant resources. Sudbury formed a little differently. The meteorite impact did the melting, but these other ones I've been talking about formed because we had lava channelization by Komatiites. Thank you.
I would like to ask the first question, and
Sure.
this being the SETI Institute colloquium, I'd like to ask about significance of this high temperature volcanism in the Archean for life, because people often talk about large magmatic provinces and how Deccan traps or Siberian traps could have affected evolution. So life was much less complex back then, but how should we imagine this time? That it was a constant large scale volcanism, or how much of the time was there?
Well,
Like
it would have been a very precarious place to live. So anytime there's lava flows covering it, if you've been on Hawaii or seen the photos of Hawaii, it's pretty barren, right? And it takes things a while to grow back. So that would have all been quite hazardous. Of course, it depends on how you interpret some of the literature, but some of the world's oldest fossils occur at a place euphemistically called North Pole in northern Western Australia, and those are about 3.5 billion years old, and they're thought to be preserved microfossils. So life was starting to come along. There were lots of algal mats around. They formed things that we call stromatolites. They're little bulbous things that represent algal mats. So there are lots of those. So the Komatiites we're talking about, 2.7, or well after that. So there would have been lots of that sort of life around. Things didn't become more complex, though, in terms of life until basically the end of the Precambrian. That's the definition of the Precambrian, which is about 600 million years. That's a long, long time later.
Thanks, Mike, for a great talk. So, are there any Komatiites associated with the Sudbury impact at all? No, right?
No,
okay,
no.
all right. And do you have any theories on why the peak at 2.7 billion years old for Komatiites? What's your favorite?
Yeah, I mean, lots of people have thought about that. I think it's basically a pot boiling event, and we have several of these. There was also one at 1.9 GA, and sort of one at 1.2. And I think what happens is that you, just like if you watch your pot on your stove, or if you were able to see into your tomato soup, you'd build up a boundary layer at the bottom of something that becomes hot, and then what'll happen is it'll begin bubbling up because the density is less. And so I think what happened is we formed a big layer at the bottom. So this is not the D double prime thing, but a layer at the bottom of the mantle, and it accumulated there for a while, and then it became unstable, and it came up. And when it did that, it did it globally, because we have these 2.7 GA Komatiites and associated basalts. Actually, the basalts are more abundant all around the world. And so I think things then settled down. We then accumulated some more heat. It wasn't as hot by then because D double prime had formed. And then we did it again at 1.9, again at 1.2, and I think there's another one at 0.6 or something like that. I guess. I don't. Yeah, I guess. I'm not very familiar with Venus. Yeah.
Hi. So I was looking at your equations. I was thinking about things like the coefficient of friction, and that got me thinking like Olympus Mons on Mars and other volcanoes on Mars where the gravity's very different, and so that would affect the coefficients. And I was wondering how your equations might apply to understanding the ancient Martian landscape when it was volcanically active.
Yeah, I haven't done that personally. David Williams, who's one of my PhD students, he's now working on it. He's actually a planetary geologist. So he worked with Ron Greeley before he died, and he's I think he's been one of the mission guys for some of the Mars things. So I think he's working on that. There's a fellow here, Enzo Cataldo, who's giving a poster on Thursday. And I think he's trying to do a comparison of planetary and non-planetary, Earth and other planetary systems, but I haven't seen the result. Yeah, but everything would be different. Gravity would be different. The temperature would be different. Coefficient of friction, I mean, everything would be different. And I think people have thought, you guys would know this better than I, that there are actually some ultramafic lavas that were erupting on Io a while back, and that they actually captured them, imaged them. Yeah.
Okay, just to understand, but in the earlier part of your talk, you mentioned these massive olivine bodies form the main channel.
Yes.
And so is there, I'm not quite sure I'm getting the relationship between the nickel concentration occupying that area. Are we seeing nickels becoming preferentially concentrated in these in a magma, which is now eliminating and erupting olivines, and then finally, in some late stage, this remnant body of yet to be erupted nickel-bearing material then occupies that channel? Is that sort of a thing of?
No, so the logic goes a bit like this. So in order to accumulate lots of olivine, okay, you have to have lots of magma flow through, because as soon as you crystallize some olivine, then you deplete the magma in the elements that go into the olivine. So what happens is because the composition of the olivine, it does change, right? We saw that in one of the figures I showed, and it changes in all of them that we have fresh olivine in. Then what happens is that, but it doesn't change enough to represent closed system fractional crystallization. So it isn't as if you just, like Sudbury, for example, an impact melt sheet, crystallizes from the bottom up. If you do a mass balance, the bulk composition of the whole melt sheet with the norite and granifier adds up to be the original quartz diuretic magma. The things we're looking at weren't closed systems. So we had lava flowing through, continually pumping. It cools at the same time as it's flowing, and it's crystallizing olivine at the bottom, and it builds up thicker and thicker and thicker and thicker and thicker. Now, the connection of the ore deposits is interesting, because, and that's a really good point actually, is that intuitively it's not absolutely necessary that flow keep flowing, because it's already made the ore deposits, because they're at the bottom. So it's melted the sediment, melted the sulfide that was in the sediment that had no metal in it. The metals reacted with the magma. It's now formed the ore deposit, and it's being covered by the olivine. But there's no reason why the lava flow had to keep going. But it did for some reason, because the eruption was very large. If we look at the bigger scale, what happens is in these eruptions, the flows get thinner as we go up, and they also become less magnesian as we go up with less olivine. And also what happens is that the flows are generally separated by interflow sediments, indicating time intervals, as we go up through the sequence. So what happened is the flows were larger volume and more episodic initially, and then when the system got going, then they became more continuous, right? But the flow rates were lower. And this is typical of many volcanic systems. And the stratigraphy is identical at Kambalda. If you go to Canada, it's the same sort of thing, in the Raglan Belt, for example. So we've seen that same thing. So the connection is a bit weird, actually, but so the evidence that it's a lava channel is all the olivine, but there's no reason why it had to remain a lava channel. It could have been a short duration lava channel, made the mineralization, and then crystallized and formed a differentiated unit. So it could have done that, but it didn't. They just kept flowing.
So the massive sulfide was one of the first deposits in the channel?
Yes, because it's right on the bottom. In fact, we think that helps erode some of the footwall rocks, because it's dense, it has a viscosity that's about an order of magnitude less than the silicate melt, even though a komatiite has a low viscosity. So it would have been more like water, and the komatiite would have been more like olive oil. And it's able to penetrate down into the fractures and erode the rock very efficiently.
Okay, I'm curious about these pot boiling events which you mentioned that seem to start, with 800 million years between them, and then they're down to 600 million years. And the last one was 600 million years ago. Are we due for another?
I don't know. That's not really my area. There are times in Earth's history where there have been very large amounts of lava erupted. So the Permo-Triassic Siberian traps, for example, in the northern part of Russia. There's actually ore deposits associated with those too. And that's thought to have been a major driver for a mass extinction event at that time, because what happened is the lavas came up, they were basaltic in this case, they intruded a bunch of evaporites and then released huge amounts of SO2, and there was also CO2 when they formed the ore deposits, and because they had to convert the sulfate to sulfide. And so that's thought to have been the driver for the mass extinction event at that time. Permo-Triassic, yeah. Yeah, right on the boundary, which was defined based on the extinction, because done by the paleontologists in the old days before they knew the absolute dates.
Yeah, so if you have further questions, you should come up here and ask Michael directly. And I would like to present Michael with the SETI mug,
Thank you.
which is a solid object, somewhat amorphous, that's supposed to be holding a liquid, presumably coffee.
Yes.
So, thank you once again.
Okay, thanks.